We'll study pass filters, high pass filter and low pass filter. Let's understand what's the meaning of pass filters. If we have F1, F2, F3 up to Fn signals with these frequencies in a combined in a signal. That is generally what we have. Try to understand. When we say we have a message signal, it means it is a combination of several signals. If we are talking of sinusoidal signals, then we have n number of sinusoidal signals with different frequencies, omega 1, omega 2 up to omega n, that is f1, f2, f3, fn. Let's say our fn is less than f2, less than f3, less than fn, that is fn is the signal with highest frequency. So this is the signal, but what we want this is at the transmitter part, whatever we are transmitting. At the receiving point, don't confuse it with communication system transmitter and receiving. I am sending it from here to there. So if we want to receive signals which are higher than, let's say, f6 and higher, so a circuit that would employ certain technique by which only upper frequencies can pass, and we get at the receiver, we get signals of particular frequencies only. That is, the higher signals above certain frequency level are passed and signals below that particular frequency are attenuated. Then it is called a high pass filter. High pass filter. Okay. For example, let's say this is frequency, this is increasing frequency, and this is our receiver output. Okay, that is what we receive at the output, the voltage. So if with high frequency we receive more, that is like this, with frequency upper than certain limit, we have output signal, that is voltage or current. We have these signals in the output, but below that it is actually attenuated. Then this type of filter is high pass filter. Just reverse of it, if we want lower frequency signals to pass, then that is called a low pass filter. That is, let's say at fk, all frequencies lower than fk are passed and above fk are attenuated, then that is a lower pass filter. We also have band pass filters and band reject filters. For example, let's say this is frequency, we want from fk minus 1 to fk only. This signal should pass like this. This signal should pass and other should get attenuated. That is called band pass filter. It's not a difficult thing to do. What we will do, we'll apply here a high pass filter. That is, frequency above this can pass, and at this point, this frequency we would apply a low pass filter. That is, frequency lower than this can only pass. Then we'll have signal in a range of frequencies that can pass. So that is called band pass filter. And similarly, we can have band reject filter. That is, we can have from here to here, let's say fk minus 1, it should pass, and then from here to here it should pass. This should be rejected. What we'll do, we'll put a low pass filter here, that is, frequencies below this would pass, and a high pass filter, that is, frequency above this should pass, and this should be rejected. So that is a band reject filter. So this is the basic concept of pass filters. Now let's start with high frequency, high pass filters. Okay, so first of all, we'll start with high pass filter. We can achieve it by either RC network or RL network. Let's see how. If we have this arrangement, this is R, this is C. Let this be your input voltage and this be your output voltage. That is, output is taken from here. What is the capacitance? What is the reactance of a capacitance? It is 1 by j omega C. You know this? The signal is coming from this side. as the frequency increases, overall reactance decreases. This is, you can see the frequency is inversely proportional to Xc. So when frequency increases, this decreases, and when frequency decreases, this increases. That is, according to the values of C and R, if omega is below certain value, this reactance will be very high, and this will behave as an open circuit for those signals, or at least those signals will be attenuated. So we'll have certain frequency above which we'll have most of the signals passing through it. So this is high pass filter. See, frequencies below certain value will be attenuated here, and above that value will pass through it and get into the output. So this is RC, high pass filter. Clear? And how we can have this with a inductor? Let's see. No, just opposite of it. We will have resistor here and an inductor here. This is L, this is R, this is VI, and this is V output. What is the reactance of an inductor? It is j omega L. Now, initially, whatever signal we are having, the current, for low frequency signals, this is very low. So what happens? All the current flows through this inductor and goes into ground. Okay. But as frequency increases beyond certain frequency, what will happen? This reactance, this XL, j omega L will be very high, so that the signal that is coming, this current will go into the output load. So what is happening? If we have certain frequency, let's say omega 1, so above that omega 1, the signal goes to this part, the output, and below that frequency, all signal crosses this inductor and goes to the ground. So this is with inductor, and the reverse is with capacitor. Above certain frequency, this will be very small, so that all signal goes to the output, and below certain frequency, this reactance will be very high and it will stop it. It will behave as a barrier to signals which have frequencies below certain value omega equal to omega 1. So this is the circuit of high pass filters. Let's analyze them. Okay, I am running it. What will be voltage output, V output? This will be equal to V input into this by total impedance. The ratio will be this by total impedance. That is, we have R by R plus, what is it? J omega C into Vi. Okay. And what we'll have here? V output will be V input into, this is j omega L. See, j omega L by R plus j omega L. Okay. Now, let's rub this. So, what is V output by V input? It is, if we take R out, this is 1 by 1 plus 1 by, or we can say minus j omega C R. Okay, R we have taken out, so we get R in the denominator. So you can write 1 minus j omega C R, or you can write 1 by j omega C R, whatever you wish to. The result will be same. Okay. So if you take the modulus, or you want to see the actual gain, V output by V input, the gain modulus of this, what you'll get? You'll get 1 by root over 1 square plus this square, omega C R square. This is what? This is transfer function. Okay, so this is V output by V input, 1 by this thing. But you know about time constant. If you have an RC circuit, the time constant is RC. So let's say at omega equal to omega 1, which is equal to 1 by RC, that is 1 by tau. What result you will get? Here only 1 by RC. So this will be omega 1 by omega. Okay. So I am just rubbing it. This will become 1 plus omega 1 by omega square, where omega 1 is 1 by RC, that is 1 by tau. Tau is RC, that is the time constant of the circuit. Okay, and this is your modulus, that is a value. If you want to know what is theta, theta will be equal to tan inverse omega 1 by omega, that is equal to tan inverse, just opposite of this, that is t by tau. Okay, you can have here also, if you want to see relation between this in terms of time, this will be equal to 1 by t by tau square. Okay, so this is about RC circuit. What about this circuit? V output by V input is equal to this thing, or what we can do, we can take out j omega L. Then what you will have, if you take j omega L out of this, you will have R by j omega L. So this will be 1 by 1 plus R by j omega L. Okay, now see, for RC you have written the expressions. So V output by V input, if we see the gain modulus, this will be equal to 1 by root over 1 plus R by omega L square. But you know what is the time constant of RL circuit? Time constant is L by R. Therefore, if we take omega 1 equal to R by L, that is 1 by tau, what you can write? You can write V0 by Vi is, the expression will now be same as that of RC circuit, that is 1 plus omega 1 by omega square, or in terms of time you can say 1 plus t by tau square. Okay, and theta is same, tan inverse omega 1 by omega, tan inverse t by tau. Clear? One more important thing from here is, I am rubbing all, you must have noted down all these expressions. One important thing is, at omega equal to omega 1, what we will have? That is, at omega equal to omega 1, where omega 1 is the frequency, where tau is equal to RC, the time constant. If omega is equal to omega 1, what you will get? You will get 1 by 1 plus 1 root 2, that is 0.707. That is, this is also called 3 dB value. At this value, at omega equal to omega 1, 0.707, that is the output gain will be, with respect to input, will be 0.707. We will draw a figure and then we will understand its meaning. And this is V0 by Vi. So this side we have this gain and this side we have frequency. So this is gain versus frequency curve. You'll see this is like this. That is, if this is 1, V output to V input, if this is 1, you'll have this point which is about 0.707 of this ratio. This is F1. That is, below this frequency, 70.7% of the signals get attenuated, and above this approximately this 30% passes. So this is the passing signals with frequency above F1. They actually constitute 30% of the total signals that is received at the output. This is the meaning of this. Another thing is, if you have, see, you will have signals like this. If this is for tau 1, if this is for tau 2, and if this is for tau 3, then this is tau 3 is greater than tau 2. That is, with increasing tau, the signal is more precise. Okay, that is, attenuation is very high.